Okay, so this is the stuff I wanted you to look at yesterday, and which will be review for the three of you who were away. So recall that when you are given, Hayden, coordinates, so I need to be specific now because you're both back. Done. Find me this page, page 3. Recall that when you've got coordinates, it always goes the x value first, then the y value. It's alphabetical. And x is left, right. Y is up, down. So if I is 7, -5, x comes first. So you start at the 0, 0, and you go over to 7, and then -5 means you're going down to -5. That guy right there is letter I, and that quadrant is quadrant 4. Because if you recall, this actually might be new yesterday, the quadrants go 1, 2, 3, 4, counterclockwise. So that was I. J is 7, -6, so that's just right below I. Also quadrant 4. K was -7, -3, so you're going left on the X, down on the Y. That should have been that guy right there. That's K, which is in quadrant 3. L was 9, 3, so you go over 9, up 3. That's quadrant 1, and M was -5, 2. So you go over 1, 2, 3, 4, 5, up 1, 2. And that's quadrant number 2. That is what your question number 1 should have looked like. Question 2 is going to look like this. 8, -2 is there. That's A. 8, -9 is right there. That's B. C was 9, -1, so that's right there. That's letter C. D was, wow, 9, -3. Spending a lot of time in quadrant 4. 4, 4, 4, 4. And then 2, 4 would have been right here. Boom. In quadrant 1.
Is there a reason for that?
Nope. We just were.
4, 3, 1, 2, 4, 4, 4, 4.
Yep. Flip the page. Then, on the back here, I gave you points. There are J of them. And I wanted you to give me the coordinates for all of those points. So I'll just rattle them all off. I'll do all the coordinates first, then we'll do all the... Actually, you know what? Quadrants probably are easier. We're going to go 2, 1, 3, 3, 4. Where's the letter F? 4. G is in 2. H is in 1. I is in 4. And J is in 3. So those were the quadrants. The coordinates of A were -10, 2. B would have been 6, 10. C would have been, remember, it's always X first, -8, -3. D would have been -8, -8. E would have been, I don't even know where E is now, 1, -5. F would have been 2, -4. G would have been -7 and 8. H would have been 2 and 5. I would have been 8, -2. And J would have been -7, -5. Comments, questions, concerns on any of those? This is stuff that you were supposed to see in middle school. I know some of you may not have, depending on what middle school you were at, depending on who your teacher was. Because I know, well, was Mr. Lineweber there last year? He was there? Okay, he is now no longer there. He went to Fraser now. But I know he would have, regardless of your thoughts about about him, I went to school with him. I know he would have taught you this stuff. I have greater faith in Mr. Lineweber, not present to defend himself, than I do in what you're saying right now. There's that right there. Yeah. Because your math teacher, you're going to tell Mr. Myers next year, oh yeah, Dawidoff never taught us this. And Mr. Myers will walk through that door and he said, and he'll do it loudly. Yeah, go for it. Just so we're clear, Mr. Dawidoff, because he does this a couple times a semester. Did you teach these guys this concept? And I'll say, I can show you the book and the page and my writing. And he'll say, thank you. And he'll leave. Because every year students are like, I don't think we did that. Except for one year, I'd actually didn't. Oh, once they were telling the truth. And that was, we had a snowstorm in semester 1. And so I didn't get to teach trigonometry to the grade 10s. So that actually happened. Yeah, that was last year. So I have grade 10s this year. Oh, sorry, grade 11s this year who were like, Mr. Dawidoff, I need trig. I'm like, yeah, that was my bad. Well, me plus the snow. But last year they were in grade 10. This year they're in grade 11 and they need the trig that I was unable to teach them because of the snowstorm. One time, done, and rain. Okay, then the bottom one's down here. Find the quadrant of the following points without plotting them on the graph. This is where you guys, I'm trying to teach you, Hayden's, what quadrants are positive and negative, regardless of those values. So, if this one's negative and this one's positive, that's quadrant 2. Both negative is 3, both positive is 1. Positive x and negative y is quadrant 4. Both positive is 1, both negative is 3. And I do not expect you to be able to do it, Hayden. Why is Hayden having to steal his pen off your desk? Okay. You both have writing utensils? Fantastic. Okay. So I don't expect you to do this as quickly as I just did, but I do expect you to be able to do it. Quadrant 1, both positive. Quadrant, so this is you picturing the grid in your head. Quadrant 2, y is positive, x is negative, so negative x, positive y. Both are negative, positive x, negative y. That's something you need to be familiar with, able to do in your head, just picturing a grid, knowing how the thing's labeled out. And I understand that that is not an easy task. Still want you to be able to do it. Okay, so today, the page, let's find this guy. We are working with linear relations. That word linear means you've got the root of this word linear is line. And in math, that word line is more restrictive than you guys are probably used to seeing it. Because if I drew a bunch of stuff on the board, okay, stop talking. If I drew this on the board, you'd be like, yeah, that's a line. Also a line. Just based on your math, just based on your English understanding. In math, that's a line, this is not a line. This is not a line. Hands up if you're like, yeah, I can see how some people would call that a line. It's a line. In some of you might say this is not a line.
That's a line. It's a dotted line.
This is a line as well. But there are people out there who be like, that's not a line, so much stuff.
It's in the line.
Okay? So I throw this on the board here too. I mean, and some of you are like, what kind of idiot would say that's not a line? Some of you say, of course it's not a line, it's curved. But this is teaching 120 grade 9s a year. I am aware that there are, and I think totally understandably, based on your understanding of the English language, some of you, yeah, that's a line, and that's not a line. But in math, our definitions are different, and so I want to be really particular about what we do. Yes, that's right. Now is not a great time. But if your bladder is going to rupture, I suppose you may. Is your bladder going to rupture? Okay. Okay, so here we go. Linear relations. What this means is, I need some colors. In math, this means our points will make straight, is that very important word, lines. Linear means, Rabin, hands to yourself, things are straight. Fine. A linear relation describes the relationship between x and y. For example, there's all sorts of different relationships. Time and distance is a relationship that exists. The amount of money you make versus how much you sold. Battery percentage versus screen usage time. These are all things that you can draw a straight line to connect conceptually. Marcus, you okay? Just tired? Okay. We can represent relationships as ordered pairs. We can represent them as equations, or we can represent them as tables of values to find out what these points are and to verify that what we have is a straight line. Now, obviously, this is going to be different. Ordered pairs, these are points on a grid. This will be the easiest to see whether or not what you have is a line. Drew some on the board. You can look at them very easily. Equations. We're going to look at what style of an equation means you've got a linear relationship. This one is slightly more difficult, but there's specific equations that represent straight lines. We're going to look for those. And tables, I don't even know why I wrote that there. Why did I draw the arrow? Y equals something times x plus question mark. Believe it or not, this kind of equation represents something linear. We'll look at what these pieces mean. And a table of values. You guys, hands up if you're familiar with a table of values. Okay? Some of you just don't want to raise your hands. That's cool too. A table of values looks like this. It's a T-chart. One column represents X, one column represents Y, and you shove a bunch of numbers in there. There is a particular rule for determining, there is one rule for determining whether or not this is linear without actually going and having to draw it. And so we're going to look at all these pieces. Okay, so which of the following graphs represent linear relations? This one I think is fairly straightforward. Is that thing a linear relation? It's a straight line. Yes, this is. It is a straight line. This one? Yes. This one? Also yes. Because if I wanted to draw a straight line through those dots, could I? Yes. We have the language to represent how this and this are different from this. Okay? These two have lines drawn through them already. So the language we use to differentiate these from this is that we say these two are continuous. Because the line flows through all of the points. Not only are these points part of the line, but everything, every little dot that makes up the line itself is also part of the relationship. So every single one of these like fractional values, all of those values are part of it when you have a line. Same thing here. We say this one is also continuous. This one, when I've just got a bunch of dots, this one is not continuous, but we're not going to write the words not continuous. We have another word that means not continuous. But it is linear. Yes, it's linear, but the word we use is, does anyone know what the English word is for like separate individual objects? It's not separate, it's not inconsistent. Because they are consistent. The distance between these ones it's always the same. Boom, 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 boom. But there's an English word. It has two meanings. One word is separate individual objects, and the other meaning is you're trying to be suspicious and hidden. The word is discrete. Discrete. Discrete in English has two meanings. It means you are trying to be sneaky, so people don't necessarily see what you're doing. People are suspicious of discrete people. But discrete also means individual separate objects. And when you don't have a line drawn, you have to ask yourself, am I allowed to draw the line? For example, let's create a relationship here between X and Y. Let's say that, I don't know, Y represents, well, forget where the grid is. Let's say that Y represents, ignoring these grids, the number of slices of pizza you have that you order and your cost. Are you allowed to have any fractional amount of slices of pizza? Can you go to Fresh Slice and say, I want 1/16 of that slice there, and I want you to shave a little bit off that guy there? Can you get any fraction you want at a place like Fresh Slice? Can you? They have pre-sliced pieces. You show up at Fresh Slice. If you've never done this, shame. You show up to Fresh Slice, you say, I want that piece, I want a piece of that one and a piece of that one. So, okay, I'm going to charge you this much per slice, and I would be shocked if the pizza guy would be like, oh yeah, I just want like a 1-inch sliver of that guy there. Like, okay, it's not going to happen. It's not going to happen. You know, I will meet you at the mall on Saturday. It won't happen. If you're right, I'll buy you lunch. If I'm right, you buy me lunch. Here's pizza. Okay, so there are things, or okay, another example would be like, this is a terrible example because you guys don't do this anymore, but back in the day we bought CDs. You can't go to A and B Sound anymore because it doesn't exist. But growing up, I would go to A and B Sound like, I want to buy these 4 albums. I couldn't go and be like, guys, I want 3 of these whole albums and I want that half CD. Okay, snap the thing in half. Now here's your half of an album. I only want the first 6 songs. I don't want to pay for the whole album. You can't do that when you're buying objects, or like, I don't want to buy that whole book. I just want the last half, because all I just care about how it ends. You can't walk into a bookstore and rip off the front half and then pay less. So these are examples of discrete objects. Okay, there are degrees to which things are discrete, but in general, discrete means there is a gap between the values you are allowed to have, and that'll be based on the context of the problem. So this guy here, continuous. Could I draw a straight line, one straight line through it all? No, not linear, but it is discrete. Not linear, but it's discrete. How about this guy? Is that a straight line? No, it is not linear, but it is continuous. And then the last guy here, yes, it is linear. And what kind of linear? Discrete linear. Okay, here we go. Next example. How much do we got here? Oh, we got a whole bunch of stuff. I'm not sure we're gonna get through it all. Here we go. Example 2. We want to graph the relation that represents the following table of values. Okay, let's graph the thing. This is the table of values. When you're given a table of values, a full table of values is nice and easy to work with. What you need to be able to identify is that this is an ordered pair. I could write this thing as the coordinates -6, -4. So each one of these is just going to be a set of values. We can go through and we can take a look at what these things look like. Let's plot them. So -6, -4 is going to be -6 in the x, -4 in the y. It's this guy right down there. -3, -1 is going to be that guy right there. 0, 2. So 0 on the x means, well, 0 is the origin, and we're going to go up 2 on the y. So when x equals 0, this is an important point. Anywhere where x or y is 0, these are we like these points. This is on the y-axis. Because the y-axis is the one that goes up and down. When x equals 0, we are on that line. We like those points. And then I've got the point 3, 5. I'm going to go over 3 in the x. We're going to go up 5 in the y. There we go. And I've got 6, 8. We're going to go over 6, up 8. Is that thing linear? Yes. Yes, it is, period. Why? Because we could draw a straight line through it. Stop touching people. With a straight line. If he's in your way and you need him to move, or if Andrew stole something from you, then ask. But don't do this, because it's not necessary and I don't know what's going on with it. Okay. Hold on, before you flip. Let's look at something interesting. We graphed this thing, we know it's linear. There was a relationship I want to look at here. Let's take a look at how these values are changing. What's happening there with the x values? Each one of them is doing what? We're going up by 3 each time, okay? So this one goes up 3, this one goes up 3, this one goes up 3, this one goes up 3. They're all going up by the same amount. Interesting. Let's take a look at the y's. What are the y's doing? Also going up by 3. That's interesting. And so what that means is if I start at this point down here, and I go up 1, 2, 3, and then over 1, 2, 3, I'm going to get to my next point. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. All these points are connected by this relationship here. Fascinating. Flip the page. Okay, so there's a mistake here. Tables of values. Do I want to do this today or do I want to do this tomorrow?
Oh, we're tired.
Yeah, well, you know. The clock's working. Okay, we'll do one more thing. Okay, so we had a table of values. We graphed the table of values. We saw that it did in fact make a straight line, and then we looked and we said, okay, well, this is interesting. The x values always went up by the same value, 3. The y values always went up by the same value. In this case, the amount up in the x was equal to the amount up in y. That's not necessarily always going to be the case, but for a relationship that we knew to be linear, we saw that the values went up at a consistent rate. Yes. What's your question? Go fast if you have to. So let's take a look at these. Now, without drawing these things, we want to see if these things are going to be linear. This is the start, but this is not everything. One thing to look at is that if both x and y values are increasing by a constant value. Okay, why are you talking? The table of values will represent a linear function or linear relationship. The constant values can be different, but if this is true, if x and y values are increasing by a constant value, the table of value is always going to represent a linear function. So we can just look at these. What's happening here with x's? In this one, x is always going up by what? X's are always going up by 1. And on this side of the table, what's it going up by? Always going, so I'm right, up, everything's plus 2, plus 2, plus 2, plus 2. So is that relationship linear? Yes. Interesting. Let's take a look at this guy. -6 goes up to -4, -2, 0, 2, 4. What's this guy going up by? We're going up by 2's all the way down. And on this side, what's happening with the y's? Down by 3. -3, -3, -3, -3, -3. So linear. You're jumping by the same amount every time and jumping by the same amount every time. Yes. Your pencil ran out of lead. What size are you working with? 0.5 or 0.7?
0.5.
Okay, I got one piece left. Come get it. You guys are Ruben. Yes, it was your bad.
Ruben.
You too. No. Hey, Hayden. Not necessary. Let's look at the last one. Here's this one. I've got -3 up to -2 up to -1, 0, 1, 2. You're going up by 1. Okay, stop. This is something that just started all of a sudden. Stop asking you guys if each other are special. Stop that now. But taking away a negative is the same thing as adding. Yes, but I'm not writing the double negative. Because I'm going to write it in simplest terms, and taking away a negative is the same thing as add. Yeah. You could. I would not mark it wrong, but I would question why you're doing more work than you need to. And I'd want to make sure you understood that taking away a negative is the same thing as adding. Okay, what's happening in the y's? Ooh. Yep. Yep. Okay, is that thing linear? No. So we've got, I'll go back to the beginning. We've got linear, we've got linear, we've got nonlinear. Here, let's do one more example. Actually, do I want to do 2 examples or 1 example? No, we're going to do another example here. What about this guy? What if I took this chart? I'm going to do 2 charts here. And I go like this. 1, 2, 4, 7. And I go 5, 7, 11, 17. Is that thing linear? Some are saying yes, some are saying no. Why do you say, Gershon, you're saying yes? Juno, you're saying it's not, because this one's going to go up 1, then it's going to go up 2, and then it's going to go up 3.
Yeah, but the other one goes up 2, then up 3. Yeah, so it's linear. No, it's not. No, it's not. It's not. That's X.
Oh, this is 6.
Yeah, I'm sorry.
Oh, what am I doing? That's up 2, then up 4, then up 6. So is it linear?
Yeah. No.
Because if I did the in-between number here, okay, so let's talk about this. And this is where I will end today. If we went up 1 here, 1 jump here is a jump of 2 here. If I went another 1 up here, if I went from 2 to 3, this side should go from 7 to 9, right? If a jump on 1 is here, is a jump 2 on here, then if I went from 2 to 3, this one should go from 7 to 9, and then from 9 up 2 again till 11, which it does. So this is in fact linear. And as a result, there is one, I said this was the start. If both x and y values are increasing by a constant value, it's going to be linear. That is always true. But there are times, don't back up yet. I'm not done this concept. This is the last concept I will do, but I'm not done it. Hey, shh. Ruben, get your stuff out. I'm not done. You know what? I am done. We'll come back to this tomorrow. You guys. Here's your homework. Guys, homework. No, forget it. You know what? No homework. I'm done. Tomorrow. We will continue tomorrow. There is no homework. We will finish this tomorrow. If you burn a writing utensil from me, bring it back, Aidens. No. Yes, but because I trust my throw. I don't trust yours.
You trust mine like this?
Yes, an underhand throw I will trust.
Can you please take off my top? I'm sorry. I won't do it again.
No, we're going back today. Because you've done it to me more than once. Yes, you have. When the bell goes, you may also go. Have a good day.
Why? We could have just walked around.
What's that?
Can we do a recess tomorrow?
A retest on what?
The one we just did.
No. Because you have to spend a lunchtime with me going through all the mistakes that you made. And unless you're going to, and show me that you've done all the work for the unit, which in a day, it's not going to happen. You both got highly proficient, so congratulations to the two of you. But you're pissed with the mistakes you made.
The usual, yeah. But I got it up so high.
No, you
I'm gonna
can't
see if
do
I
it
can go get my
tomorrow.
1-inch pizza at lunch.
You're going to walk to the mall?
Yep.
Don't be late for your class after lunch.
I'll run.
Okay.
I'll get my 1-inch pizza.
Just go ask him, hey, can I have a slice of that piece of pizza?
Yeah.
A slice of the slice. I'm willing to bet they're going to tell you no.